In this problem, we're given an undirected graph and we want to find the number of connected components that are cycles. So this sounds really complex, but it actually isn't. So a connected component is just blocks such that every node in it is connected together. So 5 is linked to 15, 15 linked to 9, 9 is linked to 11. So these 4 nodes form a connected component because they're all linked to each other somehow or some way. A easy way to think about it is 2 nodes are in a connected component is if you can reach one node from another. So from 9 you can reach 5 by going through 15, 5 or 11 or 5, but you can't reach 2. Therefore 9 and 2 are in 2 separate connected components. So the next thing is it has to be a cycle. So what does that mean? So to summarize what this says, a cycle is when each node only has 2 neighbors. So if you look at this example, the only 2 connected components that are cycles would be this one here and this one here, because this has 2 neighbors, this has 2 neighbors, this has 2 neighbors, and so on and so forth. If it has more than 2, such as this 4 here, or less than 2 neighbors, such as this 2 here, then we know that it can't be a connected component. So yeah, in the end we just want to output 2 given this graph because there are only 2 connected components. So how do we do this? So first thing first, we're given n and m, and then we're given the m edges. So how should we store these m edges? So first and foremost, the highest node number can be 2e5. So be 2e5, and let's give it some leeway of like 7. And then let's create an array of vectors, which I'll just call adjacents of size mxn. Now, what we would do is, for the m edges we're given, what we'll do is we'll store them in the adjacency matrix. Well, it's not really an adjacency matrix. So the adjacency of n dot push, we're given the 2 nodes that are connected by an edge. We read them in. Just for ease, let's 0 index everything. And then adjacency of a dot push back b and adjacency of b dot push back a, because it's a undirected graph. Okay, that makes sense. So now what we want to do is we want to remove if the number of connected components of a single node is not 2. And then once we take that away, we want to remove all its neighbors because everything in that connected component cannot be part of any answer. So let's create a Boolean array called visited to know if we have been to a node yet or not. And okay, so we go through all the nodes, and then if the adjacency, if the number of nodes it's connected to is not equivalent to 2, then we have to do, and of course we have not visited, and we have not visited this node before, then we want to make sure we've seen it because we know it can't be part of any answer. So we just run some DFS on this node. So let's create this function called DFS, which will give it some integer n, and it will visit that node and all its neighbors and all its neighbors' neighbors and all its neighbors' neighbors. So we'll visit every node in the connected component that contains this number n, and we'll make sure we have seen that. And therefore, if we've been there, then we know it can't be part of our answer. So what we have to do is, if we have not visited n, so we haven't been here before, then we visit it, and then for all the neighbors of this n, we want to visit that too. So we do DFS on this neighbor. And yeah, so this way we'll visit all nodes that are part of connected components that aren't cycles. And now that we do that, we just have to now go through the nodes that are not been seen yet, and then we know they are part of a connected component that is a cycle, and we just want to count the number of such connected components that exist. So initially the answer is 0. Oh, what's that? And then we go through all the nodes, and if we have not visited that node yet, what we'll do is we'll increase our answer, and then we'll visit all the elements that are part of its connected component. So that way we won't count a connected component twice, and then in the end we can just output our answer. This should be A, B. Okay, that's good. Okay, answer is 1, perfect. Answer should be 2. Oh, perfect. Looks good. And voila.